Electromagnetic waves including light are a fascinating and essential part of physics and the natural world. The fact that these waves do not require a medium to travel through sets them apart from mechanical waves like sound waves. This property allows electromagnetic waves to travel the vacuum of space and reach us on Earth, as I mentioned. Waves are everywhere. You are able to see the text on this module because of electromagnetic waves. A marine vessel encounters water waves. An ambulance transmits sound waves through its siren. Waves are disturbances in space and time. Most waves cannot travel in a vacuum or empty space. They generally require a medium for propagation. This is the example of waves. We have water, stadium, sound, string, and light waves.
Transmitted light refers to light that passes through a material or substance without being absorbed, allowing it to be seen or detected on the other side. For instance, when light travels through a transparent object like glass or water, it is transmitted through the material, making object visible from the opposite side. Incident light refers to light that strikes or falls upon a surface or material when light encounters an object or surface in the incoming or incident light interacts with that object, which can lead to various outcomes such as reflection, absorption, or transmission, depending on the properties of the object and the angle of incidence. Absorption refers to the process by which matter captures and retains energy from electromagnetic waves such as light or sound waves. When electromagnetic radiation encounters a material, causing its energy to be converted into other forms such as heat.
Hello. So, rainbow formation is indeed rooted in mathematics and physics. So in his work, the meteors describes outlines his understanding of rainbows, which is based on the principles of geometry and optics. He proposed that light from the sun is refracted as it enters a water droplet, then internally reflected and finally refracted again as it exits the droplet. So this process causes the dispersion of the light into its component colors, which are then reflected back to the observer's eye, resulting in the formation of a rainbow. So the rainbow formation involves the angles of incidence and refraction, as well as the concept of the critical angle. He calculated the angle at which light enters and exits the water droplets and how these angles determine the separation of the different color of light. So Descartes' approach to understanding rainbows through mathematical principles laid the foundation for the modern scientific explanation of this phenomenon. In Descartes' model, the formation of a primary rainbow is explained by a single internal reflection. With in the water droplet, which causes the dispersion of light and the separation of colors. The higher order rainbows, such as the secondary rainbow, are explained by multiple internal reflections within the water droplets, leading to further dispersion and the appearance of additional fainter rainbows. So Descartes' mathematical explanation of rainbow formation not only provide a logical and systematic framework for understanding this natural phenomenon, but also contributed to the development of optics and the study of light. His work inspired subsequent scientists and mathematicians to explore the nature of light, leading to further adva- advancement in the field of physics and the understanding of optical phenomena. Descartes' approach to explaining rainbow formation through mathematics and physics reflects his broader philosophical views on the importance of reason and knowledge in understanding the natural world. By applying mathematical principles to the study of rainbows, Descartes demonstrated the power of rational inquiry in unraveling the mysteries of the natural world. So, overall, Descartes' explanation of all rainbow formation as a result of light refraction and dispersion through water droplets, grounded in mathematical principles, represents a significant milestone in the history of scientific inquiry and our understanding of optics. His work laid the groundwork for future advancement in the study of light and the development of the modern scientific understanding of rainbows. Certainly, the wave-particle duality of light is one of the most fascinating and fundamental concepts in physics. It suggests that light can behave as both a wave and a particle depending on how it is observed or measured. This concept is best illustrated by thinking about a one peso coin. When you focus on one side of the coin, it doesn't mean that the other side has disappeared. Similarly, when physicists observe light, they can choose to focus on its wave-like behaviors or its particle-like characteristics, but both aspects are always present in some form. To delve deeper into this concept, let's consider the wave nature of light when light is considered as a wave. It demonstrates behaviors such as inference and diffraction. Interference occurs when two or more light waves overlap, leading to either reinforcement, constructive inference, or cancellation, destructive inference, or the waves. So the meaning of constructive inference is or no. So this is analogous to the ripples created by dropping two stones into a pond, where the waves interact with each other. Diffraction is another wave-like behavior of light, wherein it bends around obstacles or spreads out after passing through a narrow opening, much like waves bending around the edges of a barrier. On the other hand, the particle nature of light is best understood through the concept of photons. Photons are discrete packets of energy that constitute the fundamental units of. So when light is observed as a stream of photons, it exhibits behaviors characteristic of particles such as momentum and energy transfer in collisions with matter. This particle aspect of light is akin to the behavior of tiny, invisible entities like the individual coins in a collection. The wave of particle duality becomes even more evident when considering the famous double-slit experiment. In this experiment, a beam of light is directed at a barrier with two slits, beyond which a screen captures the resulting pattern of light. When light is sent through the slits, one photon at a time, an inference pattern, characteristic of waves gradually emerges on the screen. So even when the light is sent through one slit at a time, the inference pattern slit still appears, as if each photon is somehow inferring with itself. This phenomenon underscores the dual nature of light as it exhibits wave-like inference patterns even when its particle-like behavior is obscured. The implications of the wave-particle duality extend beyond light and have profound consequences for our understanding of the behavior of fundamental particles in the universe. In fact, similar duality is observed in the behavior of electrons, protons, and other elementary particles, suggesting that the nature of wave-particle duality is a fundamental property of the quantum world. Moreover, the wave-particle duality has played a role in the development of quantum mechanics, a branch of physics that describes the behavior of particles at the atomic and subatomic scales. Quantum mechanics provides a framework to understand and predict the behavior of particles by considering both their wave-like and particle-like as attributes. This has led to revolutionary technologies such as semiconductor devices, lasers, and quantum computing, which rely on a deep understanding of the dual nature of particles at the quantum level. To sum up, the wave-particle duality of light is a hallmark of quantum physics, challenging our understanding of the natural world. Much like observing the two sides of a coin, the duality teaches us the light. And indeed, all particles exhibit a dual nature that encompasses both wave-like and particle-like behaviors. This profound concept continues to shape our understanding of the universe and has led to transformative technological advancements that have reshaped our modern world.